Today, on the second day of this workshop, we speak about microscopy. Our first speaker will be Bob Glaeser from Berkeley, who stepped in on short notice to introduce TEM instrumentation. Originally from Downing, agreed to give this talk because he can't get out. So we have Bob Glaeser, who now committed to, I think, 3 talks. Plus a chair session. And thanks a lot for being available for this. And let us do the intro about sample preparation, you will see that. So yesterday we started the computer practicals, and the other 2 practical things. Ansgar Philipsen is sitting in the corner back there. He's the developer. Andreas Schenko is also here. The IPLT software, if you have questions concerning that, you should just harass him and ask him, for example, to help you install IPLT on your personal computer or so. With the 2DX software, you're welcome to contact me or Brian Gibson, who was sitting in that corner yesterday, if you want to have that on your own computers. Okay, so then let's start with Bob Glaeser to introduce the instrumentation we need to collect the high-resolution data.
Thank you. I suppose some of you know the old TV program, Saturday Night Live. I'm sort of my age. So my joke has been ruined, however. I was going to say, I'm Ken Downing and you're not. But I'm not either. So you understand that Ken was not able to come. But I'm using many of his slides, and of course, many of which didn't stop.
Is it still working? No, it's me here.
Ah.
Trying to use okay.
Oh, okay. Can you hear if I talk to this tone voice? Good. Okay. I'll try some of Ken's slides. So there's a whole lot of very routine things that this talk is supposed to cover, just to make sure everybody's on the same page. If there's anything that's unclear or anything you would like to know more about, don't be bashful. Shout out or catch my attention somehow. So some of this is very basic, and we'll build up some things that are very timely. The electron microscope, of course, has to operate in a pretty good vacuum, typically 10 to the minus 6 torr. A torr is roughly 1,000th of an atmosphere. So 10 to the 9 of what atmospheric pressure is. In modern microscopes, this is accomplished normally with using ion pumps for the upper part of the column. There would be a cryo trap, which we normally call an anti-contaminator. And the lower part of the column may be pumped by a diffusion pump, which is backed by an oil-based rotary pump. The thing that's important about vacuum systems is it doesn't have to be, well, sometimes it needs to be quite high vacuum in order to protect the type of gun that you're using, which I'm going to talk about in another slide. I'm not sure if it's that contact or battery cable, but the thing that we care most about is a clean vacuum rather than a very high vacuum. And the contaminants that we care about the most in the vacuum are water vapor if we're working with a cryo sample. So the anti-contaminator, if it has an efficient design, will catch most of the water vapor, but still water condensing on the specimen, as you know, is a problem. And any pump oil or other organics that may come from your fingertip or from your body odor or from the pump system, any kind of oil or contaminant is something that you would like to avoid. And as a result, the trend in some modern microscopes is to use so-called turbomolecular pumps for the specimen chamber and for the film camera. And that's considered to be, really no practical technology that can do better than that at the moment. Some nice kinds of rules of thumb to remember and important issues to remember. At the normal column vacuum, say 10 to the minus 6 torr, whatever residual gas is there, it might be oxygen or nitrogen, but it could be some water vapor, hits any one surface with enough molecules to make a monolayer if things are going to stick. And water will stick at cryo temperatures with a sticking coefficient almost 1. So if the pressure is 10 to the minus 6 torr, you build up a monolayer per second, which is pretty fast. Diffusion pumps normally bring all gases to 10 to the minus 6 or 10 to the minus 7. Ion pumps do 2 to 3 orders of magnitude better, but you want to make sure you get as much water out first before you turn on the ion pump. The turbo pumps also do quite well, a little better than diffusion pumps, are about the same. And cryo traps are very good for water, but they can become saturated and lose their efficiency in trapping water after enough has been condensed. And I already mentioned that the rotary pump or roughing pump and the diffusion pump are both, it's absolutely inevitable. There will be backstreaming of oil. It will get into your vacuum system. Turning a little more attention now to the types of electron sources. The standard design, you can hardly find it actually. You shouldn't call it the standard design anymore. Most microscopes, people don't want it. It's just a tungsten hairpin. And in his slide, Ken had remarked it is as hardy as a light bulb. I modified it as hardy as a too bright light bulb. You know what happens to a light bulb if you run too much current through it, you burn out the filament. And that's, those of you who haven't had the pleasure of burning out the filament in your tungsten filament electron microscope won't know why this humor is such an ironic comment. So tungsten hairpin filaments are pretty much on the way out. Lanthanum hexafluoride gun that has a brightness. I haven't defined that term yet, but I think I may a little bit later. 100 times that of the previous workhorse. And I think the industry was reluctant to go from the tungsten, from the light bulb filament to a little better gun because it needs a better vacuum. But that's relatively easily engineered. It adds to the cost of the microscope. But operated properly, such filament will last for a year, possibly more. The real state of the art is a so-called field emission gun, in which, so I should have mentioned the brownish orange material is compound of lanthanum and boron, lanthanum hexafluoride, that has a low work function, and that's why it is a brighter source. The field emission gun goes back to pure tungsten, but has welded into it a little wire that has been etched to a very sharp point. And then there would be some extraction voltage at the plane below the tip that most of the field gradient is confined to a very sharp tip of the etched tungsten wire. And so for a fairly modest extraction voltage, the field gradient at the tip is so high that electrons are able to tunnel out of the tungsten. In the most practical implementation of this, the whole assembly is heated by passing a weak current through this hairpin. Not enough to burn it out, as would happen in a light bulb, but enough to promote electrons to somewhat higher energies to make it easier for them to tunnel. Field emission gun needs even better vacuum than the Lab 6 gun, but it lasts for many years. Normally it's some strange accident that causes it to fail, not anything having to do with the normal conditions of work. Yes?
A question, you mentioned that this is the FEG is about 1,000 times brighter than the helping.
No, it's 1,000 times brighter than the tungsten.
Than tungsten.
Yeah, about
So it's
10
more than
times
than
the Lab 6. Yeah.
Is this on the same coherence condition? Because some of the people, when they do the six-section sample, they still believe that LAP6 has a more brightness than the FAB. If you just talk about the reticle brightness, or
So there's two important points that your comment is, or the question is bringing up. One is brightness, and we should use the scientifically correct jargon when we say brightness, but most of us, myself included, think of common sense. The image looks more brilliant, more bright, more intense. But brightness is a scientific term that has specific meaning, which is the number of electrons per second per unit area, but per steradian of solid angle. And so it's the steradians that determines the spatial coherence. Will we be talking about spatial coherence later? So it may come up later at this moment. So the Lab 6, excuse me, the FAG is brighter, and therefore, for the same number of electrons per second per unit area, it will be more coherent because it has higher brightness. There is an unresolved argument between Dieter and myself from a day or two ago, in which I insisted that there would be more current in the Lab 6, or even in the hairpin, more electrons. But it is not brighter, and it's not more coherent. The definition then is more coherent. What your colleagues may have been looking at with sections is the amount of area that, for a largish area being illuminated, it is a more intense image. And that would be because these guns can draw more current than that one can. And if you want to illuminate a large area, then you need a lot of electrons. But it won't be more coherent.
So, Bob, when you use the term tunneling, that's just the release of electrons from the tip, is it? And if so, why is the term used?
The term is essentially a quantum mechanical term, tunneling. And it means that things like electrons can pass through walls, even though that would be classically forbidden. So it's a little like teleporting. It's a quantum mechanical effect. If the wall is thin enough, and if we think of having to overcome a potential energy barrier, if the barrier is not too high. So classically forbidden for that electron to leave the metal, but quantum mechanically it can. And so you want a really steep electric field gradient, so the potential drops from the value that's in the metal to what it is in space over a very, very short distance. So, question of what's the best voltage to use? Still a controversial topic in many circles, and people with new ideas keep coming up with new points of view. Sometimes I feel that it's better to take a very adamant, binary point of view, and in that sense, higher voltage is always better, and I will explain why it's good. But there is an exception that I do want to acknowledge immediately, that if you're using a CCD camera instead of photographic film, and if you're using higher voltage like 300 kV, the performance of the CCD is much, much worse at 300 kV than at 100 kV. It's even significantly better at 200 than it is at 300. But many people worry that at high voltage you're going to lose contrast. And it's true, you will lose a small amount of contrast. But if you understand the physics of electron scattering, then you won't let your mind be tempted to believe in things that cannot be true. If you don't understand something, you won't believe anything. But if you understand the physics, some things you won't believe could be true, so you won't even consider it. Also important is if the contrast that you're looking at in your specimen is a significant amount of it is due to the use of an objective aperture, then you must use the same diameter of aperture relative to the scattering angles for the electrons. And high voltage electrons scatter at smaller angles, so you must use a correspondingly smaller diameter objective aperture, and then everything will be the same. Now, of course, the scattering cross-sections do change. Scattering cross-sections at 300 kV are about half of what they are at 100 kV. But the singleton phase will be exactly the same. Because there's less scattering, you give twice as much exposure, and the singleton noise ratio in the image is up. So, because of those considerations, apart from use of a CCD camera, it's always better to use the highest voltage that you can have access to. The advantages, some are incremental, some are somewhat major. You could well imagine that in a sample of any thickness, even thin samples, there is going to be a certain probability that an elastically scattered electron that you would like to use to form contrast in your image will get lost because it gets inelastically scattered before it leaves the sample. The small probability of the sample is thin, but the higher the voltage, the less that will occur. If you're looking at virus particles that are 500 angstroms in diameter and you hope to get high resolution, it becomes important that the higher the voltage, then the greater is your depth of field. Or in more jargony language, the Ewald sphere is more planar at high voltage. These are essentially completely equivalent ways of saying the same thing. The weak phase approximation that we like to use for our biological samples is not 100% accurate. I will show a slide sometime in the next 2 days as a prop to make the comment that tobacco mosaic virus cryo samples, unstained cryo samples of TMD are not actually weak phase objects. They're already too thick to be weak phase objects. Not a bad approximation, but measurably deviates from being a weak phase object. Well, that weak phase object approximation becomes more and more accurate the higher the electron energy. You actually gain significantly in terms of the gun brightness that we were just talking about by operating at higher voltage. For any given gun, a FEG, for example, is brighter at 300 than 100. Can't even get them at 100. The shorter wavelength results in a better spatial coherence envelope function. And the ratio, the energy spread divided by the energy, since you go from 100 to 300, let's say, in the denominator, without changing the delta E, you have less energy spread. That's equivalent to having a smaller chromatic aberration coefficient, and you get, as a result, a better temporal coherence. So both the temporal coherence and the spatial coherence envelopes are significantly better at 300 kV than at 100 kV. There are lots of things that improve this, but detector is a big issue. So I think Dieter will be talking more about the importance of having good coherence, and I think the only thing that I picked up from Ken's slides, I wanted to use this one, that in order to achieve good coherence, you want the angle that different rays make in the beam that illuminates the sample. You want that angle to be as small as possible. So there are two things that you can achieve, that you can do to achieve good coherence. You excite C1 to as high a value as you can tolerate, because the higher you excite C1, the more dim the intensity becomes. So you have to make a compromise between coherence and how intense the beam is at the specimen. But use a high excitation. Many microscopes, this is called spot size. Use a large spot size. And use as small a condenser aperture as possible. Both effects reduce the intensity at the specimen So that's why it's extremely useful to use a field emission gun, because it's a brighter electron source. Moving to another topic, I expect all of you are familiar already with using so-called low-dose technique. For biological samples, you have to limit the dose because of radiation damage. And this is really an old example from Ken Taylor's PhD thesis, showing electron diffraction patterns from the same area of the catalase crystal. In panel A, there's been almost no electron exposure involved in finding the crystal and even taking this first diffraction pattern. Irradiate for a while, take another one, it's faded quite a lot. Radiate a whole bunch more, take another one. Some of you may see just a few weak reflections at the edge of this bright halos from the inelastic scattering. That doesn't really change. But the elastic scattering, which is the diffraction from the crystal, fades away and then eventually is gone completely. So maybe I'll discuss this panel down here first. Since we're looking at a cryo sample, you have to look at it at low temperature anyway. But if you looked at a glucose-embedded sample, you could look at it at room temperature or at nitrogen temperature. Because of the so-called cage effect, when something is frozen in water, let's say vitreous ice, ionizing radiation breaks chemical bonds, those molecular fragments. In a fluid situation, they can start to diffuse and move around. But in a solid environment, they are confined to a cage. To a zeroth approximation, you don't even know that you broke the chemical bond. And so there appears to be no damage at first, even though there is damage. This cage effect is responsible for the fact that you can use about 7 times, 5 to 10 times more electron dose at nitrogen temperature than at room temperature. And you can use twice the dose at 300 kV that you can use at 100 kV. Doesn't mean that that the ability to use twice the dose at 300 doesn't mean it's better, because there is half the amount of scattering. But the signal-to-noise ratio remains unchanged. But you don't want to use too little. You don't want to use 10 if you're at 300 kV. Yes?
Well, there's a sort of this sort of single particle analysis, but that's more of an issue. But this trade-off between the signal that you get and the dose that you give, and the also the attainable resolution that you can get. Yeah. Have you got a sense of where there is a crossover in terms of the dose that you give with the resolution that you can recover? Is there an option? Yeah.
So there's the question is, what is the optimum dose between recording before there's much damage or much fading, but then not having much signal versus using too high an exposure? And I want to give an answer in 2 stages. The first one is Steve Hayward did a mathematical analysis more than 25 years ago, I think. So if the intensity fades exponentially, you can speak of the 1/E dose. So the intensity of reflection has fallen to 1/E of what it started with. The optimal dose for imaging is 2.5 times that 1/E dose. And that's that takes into consideration that the signal is decaying exponentially. So each increment of intensity gives you less and less signal, but you keep getting a little more, versus the noise is growing as the square root of n. And so there's an optimum between these two. But there's also another way of looking at this, which is that the intensity falls with a 1/E. The amplitude, your images are proportional to the amplitude, not the intensity. And so the amplitude falls with twice that dose. Take the square root of something, the exponent, then it becomes 1/2 the exponent. So this could be explained more clearly if I had prepared a few slides to explain it, or we can do it on the board or whatever. But the bottom line is 20 is a good number to use. The high resolution things will be long gone by the time of 20, but it turns out that since the noise increases as a square root of n, it doesn't hurt that much to give too much of an electron dose. It just adds a little to the noise. The signal to noise ratio actually, so it's a curve that has a very, very slow tail going. If you really want to see more about it, look at Steve Hayward's analysis. Yeah.
So what about the signal to noise ratio independence of the acceleration voltage? If you have a higher voltage, less scattering, you still have a higher shock noise from the non-scattered electrons as a background.
So you have less scattering, so you should take longer exposures, and because since there's less, so the ratio of elastic and inelastic is almost independent of the voltage. And so although there's less elastic scattering, there's also less inelastic, so you can safely give it twice the dose at 300.
And the non-scattered electrons, don't they provide a short noise background?
That grows only as a square root, and but the signal goes linearly. So the minimum dose system have you would like to have at least 4 independent settings of all the lenses, the illumination conditions, whether the intermediate lenses are looking at the diffraction pattern or the image. So I like to search in the defocus diffraction pattern mode, low magnification mode, peek at an electron diffraction pattern to see whether it's one I would really like to record. If I'm recording an image, focus on an area to one side of the specimen we want to collect data, and then completely different illumination conditions to record the data. And of course, the focus condition is done off to one side so you don't damage your sample while you're focusing. So this slide could open a controversy. Luis Molly and Ken published something a few years ago looking at an ice-embedded bacterium, and you can see the surface layer, a periodic S layer, a outer membrane, a vestige of peptide glycan, and inner membrane, and looked at it at helium temperature and at nitrogen temperature. And the title of this slide modestly says that helium temperature often provides no improvement. In fact, your eye will tell you it's a whole lot worse to look at it with helium temperature. And I think most labs who have wanted to use helium temperature for tomography have abandoned using helium. What this slide does not show any data about is the issue, well, what about, these are quite high electron doses. Well, 15 is about what you would use for high resolution. And you start to see noticeable differences at 100 or something like that. What about the high resolution features that you would like to see? And you should not use much more dose than that. There are still some people in the world who believe that there is a significant improvement using helium temperature. This issue was addressed by a very large consortium of an international consortium in which a couple of labs made test samples. Our lab made purple membrane, glucose-embedded purple membrane, I guess Dorset made paraffin crystals. And they were sent to all the labs who had helium and nitrogen capability. And the paper, text of the paper says, there could be a factor of 2 improvement in the lifetime at high resolution at helium temperature. And the data are all there in a table. If you're really interested in this, find this paper or write me for the reference. It's a hard to access paper because it's in the Journal of Microscopy, if I remember correctly. It's not available online. But get your hands on the data and plot them. And I wanted to show the graph, and I wanted to show 2 fits to the data. One showing a linear improvement in the lifetime as you go to lower temperature, and the other showing a linear improvement to about nitrogen temperature and flat after that. And I don't think the data distinguish between those two interpretations of the results, but decide for yourself. There are many disadvantages in using helium. The specimen will condense nitrogen gas, remember, a monolayer per second at 10 to the minus 6.4, and oxygen gas. The electrical conductivity of carbon films is much worse. Liquid helium is expensive, and that's not so important, but it is very inconvenient to use relative to nitrogen. And as I indicated, most labs that are equipped with stages that can use either helium or nitrogen are only using nitrogen. Anybody wants to ask more about that or disagree with me?
Do you think that's true also of the use of trailers?
So the question is it true that the lifetime of a tree halo sample would be the same?
Or the quality of the data that you
The quality of the data? Yes, I think. Yeah, I think the quality of the data will either be indistinguishable, or they will be better at nitrogen.
That is due to carbon's conductivity, or what could that?
All of the things. There's condensation of nitrogen gas and oxygen. You don't have that problem at nitrogen temperature. This is the reason why Wa, for example, when he got his 3200, specifically had it set so that the lowest temperature would be above the temperature at which nitrogen and oxygen would condense. And then that's an insulating layer, so it contributes to charging. The carbon film itself doesn't conduct as well. Many issues. All right. Now, spot scan illumination can minimize a phenomenon that I haven't introduced yet, beam-induced movement. And that phenomenon, I think, is scheduled for tomorrow at 4 or 5, something like that, beam-induced movement. So I won't go into what it is, but in terms of some of the basics of the microscope, I think most MDS systems, minimal dose systems, are set up so it's very easy for the user to use spot scan illumination. You focus the beam as parallel as you can, meaning as small a C2 aperture as possible, as large an excitation of the C1, so this virtual source is way up here as far as it can go. Make this as parallel as possible. Focus it to a little disk on the sample, roughly not smaller than 300 angstroms, but 1,000 angstroms is quite a good size. And then use the reflector coils to scan it over the sample in the raster. Commonly, a hexagonal pattern of spots is used. Now, you might think that if we spread this beam, if you overfocus the second denser so that this crossover is above, and then the electrons illuminate a larger area, that it would be more parallel. It's true that under that condition it's more parallel at any one point, but the angle illumination from this focus spot up here varies across the sample. If you average data, say single particle data or 2D crystals from an area with an overfocused electron beam, it's exactly the same in terms of the envelope function as if you had it focused to crossover and scan with the spot scan. So the advantage of the spot scan is the coherence is the same under the illumination conditions that you're using, but you're generating stress in the sample over a much smaller volume than if you made a full field. And that's the theory behind it. At any one time, there's less stress on the sample because in the area in which stress is being generated is better confined by an unstressed surround. That may be naive, but that was the conjecture. And when the technique was tested, it gave significantly improved results. Yeah.
So why would we use 100 nanometer spot and not 30?
So if you try to use a smaller, why would you use the bigger one?
Yeah, so
Yeah.
I mean, wouldn't it be better to use smaller spots?
It doesn't seem to, the experimental results are not very sensitive to the.
So how would it
even
operate?
2,000 angstroms or 200 nanometers, you get pretty much whatever benefit you are going to get, you get it at that size.
Because the area which is lost, is that similar with?
Greater, is that issues like that were described so well in classic books like by Cecil Hall and Ben Siegel and that whole generation, and your generation doesn't read those books. But the well known by people in electron optics long time ago that you always get significantly higher coherence if you overfocus E2 than if you underfocus. You do get better underfocused, but yeah.
But in principle, you could adjust C1 conditions so that you have the same spot size.
Everything else be done. So there are many degrees of freedom, and you can get the coherence you need in many different ways. But if you need the greatest coherence, then and you want high coherence at a small area, then overfocus.
So you
This could be a long discussion.
So you see that when you go goes over time,
Yeah.
you get a better power but less coherence.
So that it must be, it isn't as parallel as you think it is. So it looks on the ray that it would be parallel. The actual how parallel is depends upon the size of that, the source size, which is now down here, which has a finite width. And any point then sees that over some finite angle alpha. Yeah.
So how would an aberration corrector in the illumination path change the situation? Then you could presumably go to very small spots without losing coherence. And then a very fast exposure time.
So I don't think that the spot size is limited by the aberration of the illumination system, unless you're going to go for 1 angstrom or half angstrom.
Yeah, but if you go
STEM, yeah.
10 nanometers, so
So I think the small spot sizes that could be realized with aberration corrector of the illumination would then have so few electrons you would never use it for yeah, aberrations are not in the illumination are not a limiting factor on my radar screen for coherence. So this is a little bit about beam-induced movement, and then I'll talk more about it later. So I've been talking about electron microscope technology, but it's really, for biological samples, it's beam-induced movement that limits the image quality. And this is an unpublished picture that was taken by Richard Henderson and myself on an F30 microscope using F10 liquid nitrogen phage and using spot scan. This is the raw Fourier transform. There's not been any unbending. Images recorded on photographic film using spot scan conditions. And if you want to, you can see a spot there. I'm not sure where the other one is. Must be, must be right here. So extremely faint spots. Never mind. Forget the faintest ones. You see strong spots at about 1.9 angstrom resolution in the image with ordinary apparatus. Now, all of our images should be that good. Physics says every image should be, indistinguishable, identical. If EM technology was the limitation. But this is the only one that I have had personal involvement with in my whole entire life that is this good. You can't do science that way. You have to get to the heart of the problem of what's happening. Just unpublished, I consider it to, it probably will not be published until we can find a way to make all of the images, every time you take an image, it should be that good. But the main take-home lesson is that the existing, decade-old technology in microscopes is capable of producing images of far better quality than what you normally get. So the last thing, and I'm not going to talk about it, I just want to point to talks that are still coming. that's important in electron microscope instrumentation is the electron detector. And Yifan Chang is going to talk about, or is supposed to talk about film and CVD when you're doing electron diffraction. There'll be 2 talks representing commercial solutions from the Tietz and Gatan cameras. And then Ken Downing will talk about some of the limitations of the current technologies, and in particular how a decelerator slow down the electrons before it hits the detector. How that's one possible way of improving the performance of detector technology. Okay.